morning. We are discussing standing waves. We had started the discussion in the last class. So, let me first recapitulate what we had done and then I shall proceed from there. We were discussing a situation where there is a stretched string, the length of the string is L and we use the variable x to denote the distance along the length of the string. So, x goes from 0 to L. The string is stretched, so it has a tension T and we consider a situation where the string is plucked. So, a disturbance is introduced in the string and then the string is let to vibrate, and we would like to study the time evolution of these vibrations that are introduced in the string. So, I had told you in the last class that the disturbance, the transverse displacement of the string, which is the disturbance in this case, the transverse displacement xi, which is a function of x and t, the evolution of xi is governed by the wave equation, the same wave equation which we have been studying. So, the evolution of xi is governed by the wave equation. So, this is the wave equation which governs the evolution of xi. Let me remind you again that xi is the transverse displacement of the string, it is the disturbance in the direction perpendicular to the string. And the constant c, which is the phase velocity of this disturbance of the wave in the string, in this case is the square root of the tension divided by the mass per unit length of the string. So, if the string has a mass per unit length mu and tension T, then this c over here is the square root of T by mu. So, we are looking for solutions of this wave equation because the transverse displacement, the disturbance is governed by this wave equation, but the solutions have to now satisfy the boundary conditions that the string cannot vibrate at the two ends. The two ends of the string are fixed. So, there will be no displacement at these two ends. Writing these down in terms of xi, this tells us that xi 0 t at all times, the value of xi at x equal to 0 has to be 0. Also, at all times the value of x xi at x equal to L has to be 0. So, at x equal to L and x equal to 0, the value of xi has to vanish at all times. So, we have to find solutions to this wave equation which satisfies this boundary condition. And we had proceeded to look for solutions by the method of separation of variables. So, in this method what you do is you assume that xi, the displacement, the disturbance, is a function of, is a product of two functions, one of x alone and one of time alone. So, xi is a function of x and t. We are using the method of separation of variables. In this method we assume that xi is a product of two functions, one of x alone and one of t alone. So, we take a trial solution which looks like this and we then plug it into the wave equation. We had done this in the last class. So, once you put it in here, the x derivative does not act on t. So, the term involving the x derivative, this term over here, gives us this t into the ordinary derivative of x, the second derivative. The term involving the time derivative, this term over here. Now, if I write xi as capital X into capital T, this time derivative will act only on capital T. So, this time derivative acts only on capital T and it is now an ordinary derivative, there is no need to retain partial derivatives anymore and I can take the function x outside. The next thing which we did in the last class was we divided this whole ordinary differential equation. So, this was the equation that we got. Now, we divided this equation by xi, which is dividing it by t into x. So, the factor of t over here cancelled out and the factor of x over here cancelled out, and you are left with the equation that 1 by x, the second derivative of capital X, 1 by capital X, second derivative of capital X with respect to the variable x, small x, is equal to 1 by c square. C square is the speed, c is the phase velocity of the wave in that medium, into 1 by capital T, the second derivative of capital T with respect to time. So, this has to be, what we see is that this is equal to this. So, the wave equation with this substitution gives us this equation, where we see that the left hand side of the equation is just a function of x, the position, the right hand side, this term over here is just a function of time. So, you have a function of x is equal to a function of time. You can vary x randomly, you can vary time as you wish, but these are still equal. So, this implies that both of these should be separately equal to a constant, and I have used alpha to denote this constant. So, what we see is that if you use the separation of variables, you get two ordinary differential equations, one where this is a constant and another where this is a constant. The constant is the same for both of these. So, let us now take up the solution of the spatial part of this equation first. So, we are going to first discuss the solution of the spatial part, the x dependence, which is this term over here. So, the equation that we are trying to solve, so let me write down the equation that we are trying to solve. The equation that we are trying to solve is this. Right. So, this is the equation that we are trying to solve. We are looking at only the spatial part, which is that this should be equal to this, which is what I have written over here. So, this is the ordinary differential equation that we are trying to solve, and if this constant alpha is greater than 0, then we can write down the solution. The solution is some constant which I will call a1 e to the power square root of alpha x plus a2 e to the power minus square root of alpha x. So, we have worked out the solution to the spatial dependence, to the spatial dependent part of the wave of the disturbance xi, and we find that if alpha is positive, it looks like this. It is one exponential, it is an exponential of square root of alpha into x, and then I have minus exponential of square root of alpha, exponential of minus square root of alpha into x. There are two terms, and we have to impose the boundary condition that this function should vanish at x equal to 0. So, we have to impose the boundary condition that the function has to vanish at x equal to 0. Let me remind you again where this boundary condition comes from. We are dealing with a situation where we have a string. The string is free to vibrate in any fashion except at the boundary points, at the two end points which are fixed. So, xi has to vanish at x equal to 0, and it also has to vanish at x equal to L. So, the fact that xi has to vanish at x equal to 0 and x equal to L should be borne in mind, and we have replaced, we have expressed xi as a product of two functions, one of x and one of time. So, if xi has to vanish at x equal to 0 and x equal to L, it implies at all values of time, it implies that this function should be 0 at x equal to 0 and x equal to L. So, we are imposing the boundary condition that x equal to this x has to be 0 at x equal to L. So, this has to be 0. which basically tells us that at x equal to 0, if this function has to be 0, it tells us that a1 and a2 are minus of each of are exactly the same and they have opposite signs. So, they have the same magnitude and opposite signs, or it tells us that x is equal to a1 e to the power square root of alpha x minus e to the power minus square root of alpha x. So, this you see satisfies the boundary condition that at x equal to 0, this is 1, this is also 1. So, at x equal to 0, these two terms cancel out. So, this function capital X is 0 at one end of the string. Now, we require to also impose the boundary condition that this vibration has to vanish at the other end of the string, which is x equal to L, the position x equal to L, and it is quite clear that you do not have a solution. It is not possible to find a solution which satisfies both boundary conditions, because the only way you can satisfy this with this particular solution is by setting this constant equal to 0, which means that there is no disturbance, which is a trivial solution where there is no disturbance. So, the situation where alpha is greater than 0 is ruled out. This is ruled out. So, this situation is ruled out, and we have to look at the situation where alpha is less than 0. So, if alpha is less than 0, that is the situation. We are looking at solutions of this equation where alpha is less than 0. So, if alpha is less than 0, it is convenient to write alpha. So, we are looking for solutions to this ordinary differential equation where alpha is less than 0. So, it is convenient to write alpha as alpha is equal to minus k square. Alpha is less than 0 and alpha is equal to minus k square. We just rename this variable. Since it is less than 0, we can write it like this, where now k is positive. With this substitution, the equation governing capital X now becomes so, this is the differential equation governing the evolution of capital X, which is here the x dependence of capital X, the same equation, just that I have replaced alpha by minus k square. Now, this differential equation that you see over here, this particular differential equation is quite familiar to all of us. We have discussed this differential equation right in the first lecture of this course, and it is quite clear that this is the equation governing the simple harmonic oscillator. The position of the simple harmonic oscillator here has been replaced by this variable capital X, and time has been replaced by this variable small x. So, this is nothing but the equation governing a simple differential equation for a simple harmonic oscillator, and the solution could be written in terms of either complex imaginary exponentials, or you could write it in this fashion. So, this is the solution to this differential equation which governs capital X. Now, let us impose the boundary conditions. So, the first boundary condition that we will impose is that the function x should vanish at one end of the string which corresponds to x equal to 0. So, this is the first boundary condition that we are going to impose. So, with this boundary condition, let us see what does it tell us. So, we want this to be equal to 0, and let us see what this tells us. This basically tells us that the phase psi over here should be either plus minus pi by 2, right, which makes this into sine. So, what we can say is that with this boundary condition implies that the phase psi has to be plus minus pi by 2, which allows us to write this as sine kx. right, and this is guaranteed to vanish at one end of the string x equal to 0. It satisfies this boundary condition. So, this boundary condition basically sets the phase. Now, we have to impose the next boundary condition, which is that the vibration should also vanish at the other end of the string, which corresponds to x equal to L. So, we would like this function to vanish whenever x is L. Now, sine we know the sine function becomes 0 whenever the argument becomes a multiple of pi. So, the boundary condition tells us that k into L x equal to L should be a multiple of pi n times pi, where n could be any integer one, 2, 3, etc. Okay. So, we have obtained the solution of for the spatial part of the disturbance xi, and the spatial part of the disturbance xi is some constant into sin kx, where k into L has to be an multiple of pi, or I could write this in the following way, where k should be a multiple of pi by L. K is of the form n times pi by L, where n could be any integer 1, 2, 3, 4, etc. And for any such k, you will have a solution to the differential equation we are trying to solve, to this differential equation, which satisfies the boundary condition that it vanishes at x equal to 0 and x equal to L. Let us now work out the time part of this of xi. So, the time part of xi, let us go back to the original expression. So, we had from the wave equation, through the substitution of through the method of separation of variables, we obtained this expression. The left hand, the term over here is a function of x, the term over here is a function of time, they are both equal. So, they have to be equal to separately equal to a constant, and we have solved this particular equation where this is equal to a constant, and the constant we saw has to be negative, and it has to be, so we wrote it as minus k square, and we found that k has to be a multiple of pi by L. Now, let us see what that implies for the time part. The time part of this equation now becomes dt by dt square is equal to, now the constant alpha we wrote as minus k square. So, we can write this as minus k square Cs square into t. Again we find that the time dependent part of xi, also satisfies exactly the same equation as the simple harmonic oscillator. This too is a simple harmonic oscillator equation, and the solution for this is again well known. So, we can straight away write down the solution. It is of this form, a constant into cos Cs into k into t plus some phase phi. The phase phi and the constant c will be determined by the initial conditions of the vibration. So, let me now put together the x part of the solution, the spatial part of the solution, which is here. We have we have simplified it, and the spatial part of the solution is given over here after the simplification. So, let us put back the spatial part of the solution and the temporal part of the solution and obtain an expression for xi. So, what we see is that xi, the disturbance in the string, is of this form: a n sine kn into x cos omega n t plus phi n, where kn is equal to n pi by L, omega n is equal to Cs into kn. N could have any value, any integer value, 1, 2, 3, 4, etc. So, what we found was that the disturbance I, which satisfies this boundary condition that it has to vanish at the two ends, has many solutions. So, there are many possible solutions. There is a different solution corresponding to each integer n. So, n equal to 1 gives you a particular solution, n equal to 2 gives you a different solution, n equal to 3 gives you another solution, n equal to 4 gives you another solution. So, corresponding to every integer there is a different solution to the wave equation which satisfies the boundary condition that the vibration disappears at the two endpoints. And the solution corresponding to any value of the integer we can write in terms of an amplitude a n. I am maintaining a subscript here to show that we are looking at the solution corresponding to a particular value of n. If I change n, I will get a different solution. So, a n sin k n. So, corresponding to any integer there will be a particular value of this k, and the allowed values of k corresponding to different integers are multiples of pi by L. So, n equal to 1 will be 1 times pi by L, n equal to 2, k n will be 2 times pi by L, n equal to 3 will be 3 times pi by L, etc. This spatial function will be multiplied by a temporal time dependent function cos omega n t plus phi n. So, phi n is the phase which is determined by the initial condition, omega n is Cs, or C, here I have been using C. So, let me get rid of the S, it is C into k n. C is the phase velocity of waves in that medium, the square root of T, the tension divided by mass per unit length, that is C. So, the time part will be omega n, where omega n is C into this k, the wave number k, plus some arbitrary phase phi n which is decided by the initial condition. So, I could have many possible solutions, each one corresponding to each integer. So, there will be a particular solution corresponding to n equal to 1, a solution corresponding to n equal to 2, another solution corresponding to n equal to 3, etc. Let us look at these solutions one by one. So, the first solution that we look at is n equal to 1. So, what you have to do is you have to fix n equal to 1, put in all the values. A n will be, A1 will be some arbitrary amplitude decided by the initial conditions, phi 1 will be some initial phase, arbitrary phase decided by the initial conditions, and then you have to put in the values of k n and omega n. So, let us do the exercise and we can discuss it then. So, what we have is xi x t is equal to A1, the amplitude, into sine so k1 is pi by L. So, this becomes pi x by L into cos omega. So, omega is going to be C pi C into k1. So, C pi by L into T plus phi 1 let me set it equal to 0. So, this is the solution corresponding to n equal to 1. This solution is called the fundamental mode of vibration. It is also called the first harmonic. Of the vibration. What does this vibration look like? So, let me plot it for you. At t equal to 0, this cosine term has a value 1. Let me choose the amplitude A so that it also has a value 1. So, at t equal to 0, this is sine pi x by L. So, it vanishes at x equal to 0, it also vanishes at x equal to pi, and this is shown over here. So, this curve over here, shows you the disturbance in the string corresponding to n equal to 1 at the initial time t equal to 0. Let me repeat again, we are considering, so we have seen that corresponding to every integer you have a different solution of the wave equation. So, we are considering the solution which corresponds to n equal to 1. This solution is given over here. We have set the phase to 0, the phase is decided by the initial condition. We have set the amplitude to 1, and we are looking at the situation where we want to see the disturbance as a function of x at the time t equal to 0. At the time t equal to 0, this cosine term has a value 1, and the disturbance is just given by sine pi x by L, which is what is shown over here, the curve on top. So, this is what the disturbance in the string will look like. So, the string will actually look like this, the undisturbed string is what is shown over here. At t equal to 0, the string will look like this. Now, as time increases, this argument over here is going to increase, and we know that as t increases from 0, the value of cosine of this thing over here is going to fall. So, the value of this cosine term is going to fall, this term is going to remain as it is, and this is 1. So, the value of cosine over here falls, and at a later time, slightly later time, this is the string, this shows you the position of the string at a slightly later time. So, this is t equal to 0, and this is at some slightly later time. And then as t increases further, when this whole argument becomes pi by 2, right. So, you can calculate the time required for this whole argument to become pi by 2, not very difficult. So, when this whole argument becomes pi by 2, the value of cosine pi by 2 we know is 0. So, the displacement of the string becomes 0. So, this is when the argument of the cosine term, this over here is when the argument of the cosine term becomes pi by 2, and the cosine term gives you a 0, the string is in the undisturbed position, the displacement of the string becomes 0 everywhere. And then again when time increases even further, this crosses pi by 2. So, the cosine term has a negative value. So, this will be the position, the disturbance in the string at a later time, and finally, when it becomes pi, when this argument over here becomes pi, this value will be -1 and the string will be here. When it crosses pi, again the value of cosine is going to tend to 0. So, the whole thing is going to repeat. So, the string is the string initially was disturbed to this position, it is going to go down as I have shown by the arrows over here, it is going to come here and then again go back and forth. So, it is going to keep on going up and down. So, it will go down and then it will go up again and then it will come down again, it will keep on going back and forth like this. So, I hope this is clear to you. So, this is the solution corresponding to n equal to 1. This is called the fundamental mode or the first harmonic. Let us also ask the question, what is the frequency, what is the wavelength of this disturbance in the string. So, you can look at this, k has a value n equal to 1, k has a value pi by L, and 2 pi by k gives us the wavelength. So, what you see is that for n equal to 1, n equal to 1, you have a wavelength lambda 1, which is 2L. What is the frequency of this vibration? So, omega n, omega 1 is c times k 1, omega divided by 2 pi gives us the frequency, k 1 we know is pi by L. So, I have to divide it by 2 pi. So, the frequency nu 1 is c So, omega divided by 2 pi, this is pi by L. So, if I divide this, put pi by L here and divide it by 2 pi. So, the factor of pi will cancel out and I will have c by 2L. So, the fundamental mode or the first harmonic has a wavelength which is twice the length of the string, and it has a frequency which is c divided by 2L, where c is the phase velocity in that string. Let us now consider the solution when n is equal to 2. So, this is the expression for the disturbance in a general situation. Let us now consider the solution when n is equal to 2. So, when n is equal to 2, k 2 will become 2 pi by L, omega will become c times that. So, let me write down the solution. Again, I will choose the amplitude to be 1, I will set the phase equal to 0. So, let me write down the solution for n equal to 2. I will have some arbitrary amplitude which I will set equal to 1. Now, I have sine 2 pi x by L into cos c into 2 pi t by L. I have set the phase to be 0. This is called the second harmonic. Of the vibration or the first overtone. So, let us draw what this looks like and then study its evolution. So, let me draw it for you here at t equal to 0. So, let us first set t equal to 0, this has a value 1. So, at t equal to 0, this is sine 2 pi x by L. So, we know that it will have value 0 here, it will have value 0 here, it will also have a value 0 when x is L by 2. At x equal to L by 2, the argument over here becomes pi. So, it will again go to 0. So, we are drawing sine 2 pi x by L and it will look like this. So, this is the disturbance of the string. So, this is what the string will look like at t equal to 0. At t equal to 0, this cosine term has a value 1. So, this is what the string will look like at the disturbance in the string, which you can say is the string itself. It will look like at t equal to 0. Now, as t increases, this cosine term is going to fall and the string is now going, so the amplitude of this is going to go down and it will look something like this at a slightly later time. And then at a certain value of t, which again you can calculate, the cosine term over here is going to be 0. So, the string is now going to appear like this. And then as time increases further, it is going to become negative, this cosine term is going to be negative. So, the string is going to appear like this. and then with further increase of time is going to get more negative, and you will have this pattern repeating itself. So, let me show you what this looks like. This should be not first, but oops. The second harmonic. So, this shows you the string at t equal to 0, and then as time increases this is going to go down, this is also going to go in this direction, and then at a certain time the displacement is exactly 0, and then again this is going to, this part becomes negative, this part goes up, and then it is going to become like this, and then it will become like this, and then the whole thing is going to go down again and the pattern will repeat. So, this is the second harmonic, and then you will have higher n equal to 3, 4, 5, etc. Now, I should tell you that the points where these are what are known as standing waves, that is the first point which I should mention. So, you see as the time evolves, you have the spatial pattern does not move forward or backward, right. So, what you see is that as time evolves, the same spatial pattern, the amplitude of it goes up and down, but the pattern itself does not evolve forward or backward. This is why these are called standing waves. So, the same pattern remains in the string, its amplitude goes up and down, becomes negative, and then again becomes positive and negative and 0. So, the amplitude oscillates, but the pattern itself does not move either forward or backward in the string. So, this is why it is called a standing wave, the standing pattern, okay, or a stationary wave. The same pattern just goes, the amplitude of the same pattern just goes up and down with time. That is what happens over here. The wave does not move forward to the left or to the right, which is why it is called a standing wave. In this standing wave pattern, there are places where the disturbance has a maximum value, and there are places where the disturbance has a value 0. The place where the disturbance is 0, it remains 0 throughout, right. So, there are certain places, points where the disturbance remains 0 throughout. These points are called nodes. So, in this situation we have a node over here, we have two nodes at the two endpoints, and we also have a node over here. So, n equal to 1, we only have nodes at the endpoints which are fixed. N equal to 2, we have one more node at the center, in the center. N equal to 3, you can guess it will look like this. There will be two nodes in between, and the whole disturbance is going to look like this, and the amplitude of this disturbance is going to evolve with time. So, at a later time instant, the amplitude is going to go down, it will look like this, and then at a certain time the amplitude will become 0, and then it will become negative. So, the whole pattern will get inverted, it will look like this. So, these are the nodes, the value of the disturbance here continues to be 0 throughout the vibration. So, these are called nodes, and the point where the disturbance is maximum are called antinodes. Let us also ask the question how the wavelength of the vibration changes as I vary n. So, we have already seen that for n equal to 1, the wavelength is 2L and the frequency is C by 2L. Let us now look at the situation where the n equal to 2, or we could just use this over here. So, K2, we have K2, so there is going to be a factor of 2 over here. 2 pi by K gives the wavelength, So, when n equal to 2, the wavelength is L, right. N equal to 2, the wave number is 2 pi by L. 2 pi divided by the wave number gives the wavelength. So, 2 pi divided by 2 pi divided by L gives me L. So, for n equal to 2, the wavelength is 2 times lambda 1, lambda 1 is 2L. So, the wavelength for n equal to 2 is 2 times lambda 1. Similarly, the frequency is 2 pi into the it is the angular frequency divided by 2 pi. So, n equal to 2, the frequency is going to go up twice. So, nu 2 is equal to twice nu 1. N equal to 3, again let me show you the expression, n equal to 3, n equal to 3. So, this is going to be 3 pi by L, the wave number is 3 pi by L, 2 pi divided by the wave number gives the wavelength. So, the wavelength is 2 by 2 divided by 3, 2 by 3 into L, 2/3 of L, or what you can say is that this is, sorry, this should be lambda 1 divided by 2, and this will be right. I had made a mistake over here, it should have been this, the length, the wavelength was for n equal to 2, the wavelength was L, which is lambda 1 divided by 2, not multiplied by 2. Similarly, for n equal to 3, the wavelength is lambda 1 divided by 3, n equal to 4, the wavelength is lambda 4 is equal to lambda 1 divided by 4, and the frequency is 3 times nu 1, here it is 4 times nu 1, etc. So, for higher and higher values of n, you will have higher and higher harmonics. The higher harmonics all have higher frequencies. So, the first harmonic, which is the fundamental mode, has a frequency C divided by 2L, twice the length of the string. The second harmonic has a frequency which is twice this. The third harmonic has a frequency which is 3 times this. The wavelength is half, 1/3. The fourth harmonic has a wavelength which is 1/4 of the fundamental wavelength, and the frequency which is 4 times the fundamental frequency. So, these are called the higher harmonics of the wave, of the string. Now, this nearly brings us to the end of our discussion. There are 2 points which I should make before we really close. The first point which I should make is that any standing wave, so let me just, is actually a superposition of 2 travelling waves. So, let me show this to you. So, let us consider the two travelling waves sine kx plus omega t plus sine kx minus omega t. So, this is a superposition of 2 travelling waves. This is a right travelling wave, this is a left travelling wave. Now, this first wave we can write as sine kx cos omega t plus cos kx sin omega t. The second one we can write as plus sin kx cos omega t minus cos kx sine omega t. So, what we see is that when I superpose these two terms, the last two terms will cancel out, and what we have is 2 sine, this should be k 1 omega 1 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 k 1 omega 1. So, finally, this will give you sine k 1 x cos omega 1 t, which you see is the standing wave corresponding to n equal to 1, the first harmonic, the fundamental mode of vibration. So, what I have shown you here is that the superposition of a left travelling wave and a right travelling wave gives you a standing wave. So, any standing wave is actually a superposition of a right travelling wave and a left travelling wave. This is the first point which I would like to make. The second point which I would like to make before we end our discussion is as follows. So, let me just go back to the point where we started our discussion. So, the point where we started our discussion was over here. We are interested in following the evolution of a disturbance in a string in a situation where the two endpoints of the string are fixed, they cannot vibrate. And we found that there are solutions to the wave equation which are standing waves which satisfy these boundary conditions. Now, here I show you some arbitrary disturbance. Let me ask you the question, does this look like one of the standing waves? Right, does this look like one of these standing waves? We have seen pictures of these standing wave. The first harmonic is 0 here and 0 only at this point, it goes all the way like this. The second harmonic is something which goes up and then comes down, shown over here. The third harmonic, I have also told you, is going to have 2 zeros, and then the fourth harmonic is going to have 3 zeros and so forth. So, the question is this one of those standing waves? And the answer is no. Obviously, this does not look like sine, right. The standing waves we saw were sine k n x, this x dependence was sine k n x, and this does not look like that. So, the question is, how do we handle this? Well, the solution to this question is as follows. Any arbitrary disturbance in the string, so any arbitrary disturbance in the string can be decomposed as a superposition of standing waves with different values of the integer n. So, any arbitrary disturbance, for example, this particular disturbance can be decomposed into a superposition of such standing waves, and the time evolution of this can be obtained by following the time evolution of this expression, which is a sum of different standing waves. And this in general the sum of such standing waves in general will not be a standing wave, it will be something that goes back and forth along the string. So, let me show you first let me show you one situation where, so we have a disturbance in a string which initially looks like this. So, we have a disturbance in a string which initially looks like this. So, this is the initial disturbance in the string, the black curve over there, and this is a superposition of many standing waves with different values of n, different amplitudes, different phases. Here I have shown you one example, but it is a general mathematical fact that any arbitrary disturbance in the string, any arbitrary disturbance in such a string with the boundary conditions that the disturbance is 0 at the two ends can be decomposed into a sum of such standing waves. So, this is the initial disturbance in the string. Now, as time evolves, each standing wave, the cosine term of each standing wave is going to change with a different frequency. Omega n is different for each standing wave. So, it is going to change differently. So, this xi x t is going to look different after some time. So, this shows you this curve over here, this curve over here shows you the form of xi x t at some slightly later time. You see the form has changed, and then this shows you the form of xi x t at some even later time, and then this curve over here shows you the form of xi x t at some even later time, and this whole pattern is going to change. It will evolve with time. So, you can see that the peak has shifted over here, and it is going to evolve with time, and then after some time it is going to repeat again, and the time required to repeat again is decided by the smallest frequency, smallest value of omega n, which is there over here. Right, it is actually decided by the full so it is decided by all of these values of omega n which are here. They all have integer values. So, you can determine when the whole pattern is going to repeat. So, the point here is that we have learned about standing waves in this lecture. A standing wave pattern does not move around, it's only its amplitude changes with time. It has nodes. At nodes, the vibration, the disturbance remains 0 throughout. Any arbitrary disturbance in the string with the boundary conditions that the disturbance should vanish at the end, any arbitrary such disturbance can be decomposed into a sum of standing waves, and you can follow its time evolution by following the time evolution of the individual standing waves and adding them up together. These standing waves are very important. Say for example, if you want to look at the vibrations of a string in your guitar, the guitar we know produces sound, and the smallest frequency sound you can produce with the string is basically the fundamental mode. You will also have the higher harmonics being produced if you plug the guitar string. It depends on how you plug the string, depends on which mode you excite. These standing waves are also important. For example, if you are studying electromagnetic waves in a cavity, if you have a metallic cavity and you have an electromagnetic wave inside the metallic cavity, we know that at the boundaries on the metal surface the electric field has to vanish, right? The electric field vanishes on the metal surfaces. So, if you have an electromagnetic wave inside a metallic cavity, it has to vanish at the boundaries, and again there you have to solve the wave equation with the appropriate boundary conditions where it vanishes at the ends, and this gives you standing waves, standing electromagnetic waves inside the cavity. So, this basic idea of standing waves has various applications, and it appears in a large variety of situations, some of which we will be encountering later on in this course, and there are many more which we shall not be discussing. So, let me stop here for today, and we shall continue in the next class.